Okay, good afternoon all. In this 20-minute session, let me just have some introduction about these point sources and arrays. So, what is a point source? Point source is nothing but an antenna. So, what are the different synonyms used for an antenna? It can be a point source. Even sometimes antenna can also be called reflector, and one more word is also more frequently used for antenna. It is a radiator. All these mean the same: point source, radiator, reflector, antenna, all the means the same. So what is a point source? A point source is one hypothetical antenna. It's ideal theoretical antenna which has got no shape. It's a point, okay, and its efficiency is 100%. It radiates in all directions. You can see it here on the screen. This is a point source. The directions indicate that it is radiating in all directions. That's why it is also called omnidirectional antenna. Okay, it is omnidirectional, which radiates in all directions. It is also called isotropic antenna. Iso means same, which radiates same in all directions. Okay, it's a hypothetical antenna. Now, in the module 3, you have seen the antenna and some of the parameters required to study, because in order to design any new thing, in order to establish any new object for your usage, you should know how it behaves. You should know its properties. Then only you can experiment on it to get a new version, right? So जब तक आप पहले का सीखोगे नहीं उसमें क्या है एसेंस, आपको डेवलपमेंट स्टेज आपको पता नहीं चलेगा. What you can develop, what you can modify, what you can invent. That's why you have studied some basic antenna parameters in the module 3. So this is the continuation. Here in this module, we will be studying the array system. Basically in this module, important part is array system. So what is an array? As the title suggests, you can see it. It's a point sources and arrays. So array is nothing but the collection. So it's a collection of what? It's a collection of antennas. Different antennas all put together is called an array. And how we can develop array, how we can construct array? Array can be constructed using either same kind of antennas or different antennas. Okay, there are two possibilities. Either you use in that arrays all antennas of same type, all behaves, which behaves in same fashion, or you can take different antennas whose behavior, whose characteristics are different. So arrays, why we go for this array system? Why it is required to get this array? So arrays are basically used to increase the directivity. So in the yesterday session, we have seen for a particular power pattern, you have found the directivity capital D. So directivity is a important parameter rather than instead apart from radiation intensity, gain, efficiency, directivity plays very important role while designing an antenna. Any desired power pattern can be obtained using the array of available antennas. What is the meaning of the statement? Any desired power pattern. See, in this, there are two possibilities. In yesterday's session, I was telling you in the class, if I give you certain material to you, and if I tell you that I want to design one antenna which has got certain directivity, okay, I will give you, this is the target, मुझे directivity D equal to 5 चाहिए. I will give you some material to you, whatever is required to design an antenna. I want directivity equals to 5. So how will you start? You will first design the antenna. You will see directivity 5 लाने के लिए you do some calculations, mathematical calculations. Aperture कितना होना चाहिए उस antenna का, accordingly what shape will be suitable. You experiment it and you will design one antenna. Say this is your antenna. Assume that this is one antenna. Okay, you will design with certain specified aperture which will give you the directivity D value is equal to 5. This is one way, giving you the targets. This should be the output. This much should be your pattern. For example, मुझे ऐसा पैटर्न क्रिएट करना है। इस पैटर्न को क्रिएट करने के लिए मुझे अरे सिस्टम कैसे डिजाइन करना पड़ेगा? सो दिस इज वन पॉसिबिलिटी, गिविंग यू द टारगेट्स एंड you will work on it, you will design the antenna. This is a difficult part, okay? And one more easiest way is what you're doing now. एक सिंपल प्रॉब्लम्स आप कैसे सॉल्व करते हो? लेट इट बी एनी टेक्निकल सब्जेक्ट, एनीथिंग, नॉट इवन मैथमेटिकल, एनी टेक्निकल सब्जेक्ट। अगर आपको कुछ स्टेटमेंट्स देते हैं एक प्रॉब्लम में, यू कलेक्ट दैट गिवन डेटा, यू हैव द फ्यू फॉर्मूलेज विथ यू, उस फॉर्मूला में जो भी डेटा है आप सब्स्टिट्यूट करते हो, आपको आउटपुट आ जाता है। दिस इज सेकेंड वे। सो here also in the antennas we have two things. One is parameters and all is given to you. Antenna is already there, okay? There is one designed antenna. In that you find certain parameters, okay? एक antenna already constructed है, you have certain antenna with you, you find certain parameters. Second possibility is parameters will be given to you. I want this much to be directivity, I want this much of efficiency, I want the aperture to be this much. This is the second type where targets are given to you, you design an antenna. This is a, we call this synthesis. We create the antenna according to the deadlines, according to the targets, okay? So there are two things here. One is very straight away, just like how you solve any problem. Parameters, some data is given to you, already one designed antenna is there, some data is available, and you will find certain parameters. One antenna, how it works, that you will identify in first part. In second part, some targets are given to you. You want this much of directivity only, this much of gain only. These are very much specific. Accordingly, you will create the data. You will create the data and you will design the antenna. Okay. Now, that's the meaning of this. Any desired power pattern can be obtained using the array. So, for example, डायरेक्टिविटी मुझे इतना ही चाहिए। अगर आपके पास मटेरियल अवेलेबल है, एक एंटेना के बदले में 10 एंटेनाज यूज करके उसको आप कम कर सकते हो, मैन पावर कम करके सिस्टम को बढ़ा करके अगर आप अचीव कर सकते हो तो यू कैन गो फॉर इट, ओके? नाउ द रिजल्टेंट पैटर्न ऑफ एनी array antenna, array means what? Collection, okay? Assume we have different say 1 2 3 4 5 6, so totally 6 antennas are clubbed together. This is one array system, okay? Now the resultant pattern, each antenna will create one pattern, that is what you have studied already, called radiation pattern. Radiation pattern is one graph which will show you the variations of radiation intensity. So each antenna, यहाँ पर अगर 6 antennas हैं array system में, तो all 6 antennas will have certain patterns. So all together पूरे system का pattern कैसा होगा? So the resultant pattern, it depends on, first of all, number of array antennas used. So हम यहाँ पर 6 use कर रहे हैं, 7 8 whatever. So how many number of antennas you are using in an array, it matters a lot. Then second thing, shape of the array, how you are preferring the shape of the array system to be. For example, if you just observe, let me just discuss that. So the shape of the array matters a lot. How you're building your array, how you're positioning the array, either horizontal, vertical, whatever. And the individual pattern of each source also matters a lot. अब for example आपकी क्लास में 36 members हैं, ओवरऑल परफॉर्मेंस ऑफ द क्लास अगर हमको मेजर करना है तो इंडिविजुअल 36 बच्चों के परसेंटेज अच्छे होने जरूरी हैं, तभी पूरे क्लास का परफॉर्मेंस एनहांस होगा, राइट? सो इट मैटर्स अ लॉट व्हेन इट कम्स टू कलेक्टिव परफॉर्मेंस. When you are interested in the collective performance, it is very much important that individual performances should be good. So individual pattern of each source matters a lot. अगर each pattern का, each source का pattern अच्छा है, it is efficient, then the overall array systems pattern will also be good. Then the distance between antennas, it's an important parameter. Based on this, many problems we will be solving in the further concepts. Distance between the antennas, अगर मैं 6 antennas ले रही हूँ एक array system में, now the distance between these antennas, this matters a lot, whether you are spacing them very closely, when you are whether you are keeping all these at equal distances or different distances. You know, it's all the part of your experiments. When scientists, researchers, they do conduct certain experiments, they try this, all these trial and error method. They come to one conclusion. Before, before that conclusion, they do all these experimentations. They will keep the distances same and they'll check what is the performance. They'll maintain different distances and they'll check. So obviously the distance between the antennas matters a lot when we are designing an array system, and the resultant pattern, it depends on all these parameters. Then array dimensions, structure of each antenna, what is the size, the shape, all that matters. And also the phase difference, this comes in terms of the waves. When the waves travel across the antenna, obviously many antennas are involved here in an array system. The phase difference among this what you can say power, electromagnetic waves, that matters a lot. These are certain parameters on which your resultant pattern of an array depends on. And we have seen what is a point source. Now coming to the power patterns. In the yesterday's class, we have started with the power patterns directly. Let's see what is a power pattern. In the module 3, we have seen what is a radiation pattern. Radiation pattern, it is a graph. Okay, it is a graph which will show you, I think this example, this figure you have taken for beam area, right? So this is one three-dimensional graph, radiation pattern, which will give you the information or the variation of radiation intensity, that is capital U. Okay. In the similar manner, we will be studying what are power patterns. For that, consider a transmitting antenna. We are considering one antenna in the free space, which is actually a point source. We are not considering any particular shape. Okay, it's a square, it's a circular, anything. We are considering one point source as a transmitting antenna. Where it is located? It is located at the origin of the coordinates as shown. And the coordinate system which we use here is a spherical coordinate system. In yesterday's problems, we have seen double integrals, surface integral over u d omega. I think this we have seen yesterday, u into d omega, where d omega we have substituted it as sine theta d theta d phi, right? So for spherical coordinate system, r, theta and phi are the different coordinates. So the radiated power, whatever the power comes out of this, you can see it here in this on the screen. This is the center. This indicates your point source antenna, which is kept at the origin of the spherical coordinate system. And if you see this direction, it is indicating s suffix r, which we have used this. We have used this SR in power theorem, radial component of the power density or Poynting vector, s suffix r. So what this indicates, you imagine one ball, sphere, okay, center पे एक antenna है. This indicates, these lines indicate what? Because we are considering a point source here. So in all directions, it is radiating its power. The power is getting radiated in all directions. So this R indicates the radial distance. Hence, only the radial component of the Poynting vector we are considering. So this is very clear why in power theorem we have taken only SR. Why not theta and phi components? Because when the power radiates, when it comes out of a point source, it radiates in all directions radially. it radiates, okay, it flows radially. So the radiated power flows from the source in radial lines. This one line I can show you. Likewise, it's a point source, so there can be many lines. And the power flow per unit area, power flowing per unit area being normal, we call it power density or a Poynting vector, which is either P or S. P is equal to, we have seen this already, E cross H. Fine. Now, for a point source, the Poynting vector either P or S, it has only the radial component SR. Power radiates, power flows radially with remaining two components 0, theta and phi. Now, the magnitude of the Poynting vector, we consider only SR, not S theta and S phi, okay, because they are not existing, only SR will exist. Now, what is a power pattern? Just like radiation pattern, we should define it. What is a power pattern? So it's a graph of what? In radiation patterns, it is a graph of radiation intensity U. Okay. Here in power patterns, it is a graph of SR, that is radial component of a Poynting vector at a constant radius as a function of Poynting vector. Radial component SR, it's a graph of SR. Okay, it is called the power pattern. And if you see isotropic point source, isotropic hypothetical antenna है, अगर आप यहाँ पर point source रख रहे हैं, it radiates in all directions and not circle but sphere. I cannot draw sphere on the two-dimensional paper. So this, if this is a sphere, if it radiates in all directions equally, what angle it is covering? The angle covered is 4 pi. So the three-dimensional power pattern for isotropic antenna, it is a sphere because it radiates in all directions uniformly, which is equal to 4 pi. And अगर मैं पेपर की बात करती हूँ two dimensional, I can show it as a circle. But however, the angle is 4 pi, not 2 pi. This is what? Center point source. SR is the radial component of the Poynting vector, and after that you can just draw these lines, no problem. Only one line drawing is sufficient. And theta angle starts from 0. Why theta I have taken it here? You can see theta starts from here, right? It will go, and phi starts from here. So this is about power patterns. So if SR is expressed in watts per meter square, yesterday you have told me what is the unit of SR, power density, power flow per unit area, watts per meter square. If it is expressed like this, it is called absolute power pattern, absolute. And if it is expressed in terms of certain relative value with respect to certain reference, with respect to this direction, this much is the Poynting vector, comparative, then we call it relative power pattern. We also call it normalized pattern. Normalized value means shrink down to 1. Range is between 0 and 1. Now coming to power theorem. In yesterday's class, we started with this. So before that, in the introduction, it was actually, you should know in the power theorem, why only we are taking SR. That is important. Because if you observe this figure, here only the radial component of the Poynting vector exists. No theta and phi component. And I have already explained you this during when I was taking the beam area. A patch, a small area we considered. We have taken this two sides, how it is r into d theta, how it is r into sine theta into d phi, how it is like that. That I have already explained you. Please go through the link, you can get it. Why the area of the C is this, a into b. The sides are r d theta, r sine theta into d phi. That's why in yesterday's classes, when we solve the problems, instead of d omega, we have taken sine theta, d theta and d phi. I hope you understood this much. So power theorem we have already discussed. This is a small part, radiation intensity. It's a repetitive term. One of the antenna parameters, we have studied this already. What is the radiation intensity? U. Again, it is power flow per, the area being normal. Somewhat like that we define it. And SR, radial component, is given by power flow per area for a sphere is 4 pi r square. And if you just multiply this r square into SR, okay, remaining is P divided by 4 pi. P divided by 4 pi, it is for an isotropic point source. Remember, because 4 pi angle कब आता है? Sphere है तो. अगर आपका shape sphere है तो 4 pi angle आएगा. So if a point source is kept at the center of the ball sphere, it radiates uniformly in all directions. So when you are taking all directions, the total angle covered is 4 pi. So this P by 4 pi is actually the radiation intensity U, or U naught you take. In problems we have taken this U naught, which is actually the radiation intensity of isotropic antenna, because ये denominator में 4 pi term है, the total angle covered for a sphere. So if you see, P is equal to 4 pi into U, and in your problems you have taken this U naught. Now power patterns, that's what I said you. P is equal to 4 pi into U naught you have taken. This is the equation, second step in your problems which you use. Then problems. We have already dealt with all these problems. Any doubt in today's session?